Okay, so I've pinned the camera and spotlighted it for everyone. So is everyone seeing this view full screen?
Yes.
Okay, wonderful. Rob is making some adjustments here, cameraman. Okay, so welcome to the lab session for radiated emissions, electric field, RE102. Most of what I'm going to show are actually previous data that we took last week and on presentation slides. So not all of it will be live, but did that in the interest of time because there are several different antennas and rotating between horizontal and vertical polarization, all that good stuff. This takes some time. So in the interest of time, we just took a lot of data beforehand that I'll show you as we go through this. But we are still in the lab to do some show and tell. So we got some people gathering in the lab. Oh, Andrea. So we got some people gathering in the lab, and so I'll do a bit of show and tell before we walk through any of the data. First, you're seeing a whole lot of ways in which not to run RE102. You generally do not have a TV screen back behind your unit under test and a lot of other junk on the bench, but it's show and tell. So we'll do the show and tell here. I'll go through the different antenna types as we go through the talk here, but one that we just put in place here is the biconical or bow tie. I suppose if I had thought about it, I'd put it in horizontal orientation because that clearly shows why it's called a bow tie antenna. A little hard to see, but there you go. So that's the bow tie antenna, and one that's sitting out in the hall. The hallway is where all this stuff belongs when it's not being used. You want to minimize how much stuff is actually in the chamber when you're doing radiator emission scans. But that large antenna right there that I'm pointing at, that's the DRG, the double ridge guide horn antenna. And you'll see pictures of that when we use that. That's a bit of a beast to roll around. I mean, it's on a cart with wheels, so it's not too bad, but we don't want to move it around any more than we have to. There's also the doors are open. So these are the doors to the chamber that close when we do proper radiated emissions scans, and we'll show some differences there. These doors have to be open for me to get a Wi-Fi signal for you guys to be able to actually, hear and see what's going on here. So that's another big part of why we just took a bunch of data last week, because with doors closed, we get no Wi-Fi signal in here and we can't do the session. So practical considerations. This small double ridge guide horn antenna, and that's James. James got this set up in short order this morning. This is the double ridge guide horn antenna. You see the elements there. This is vertical polarization, as in the orientation of the elements. Sometimes when you first look at this from the side, you might think, well, this is horizontal polarization because the long dimension is what's horizontal. But no, you got to pay attention to the elements. It's the orientation of the elements. So that's vertical polarization. And with this particular antenna, and this is what we use for over 1 gigahertz, we use a low noise amplifier that just mounts onto this fixture with a very short cable right to the output. So we'll get to all of this. The same EUT that we've been using for all of these sessions. This noisy power converter with no filtering by design or by lack of design. And we'll talk about some of these other antennas here as we go through this. So that's a bit of background, and now I'll switch to the charts for a little bit to go through some of the things in there. So any questions so far? Okay, let me share my screen and go back to the beginning of this. Okay, is everyone seeing the charts?
Yep.
There we are. sometimes this little bar at the top covers up the bar in PowerPoint, and I can't control what I'm doing. So there we go. All right. So just a little bit of review from the previous session. That our dominant concern below 200 megahertz is, for the most part, cable-to-cable crosstalk. So we don't generally do RE102 below 200 megahertz. We generally assess that with direct measurements of common mode, conducted emissions, and susceptibility, which we've covered in separate sessions, previous sessions to this, in fact. So, but I'm going to show you the antennas that we use below 200 megahertz, because you should at least be aware of them in the event that you ever have to use them, because they do come up from time to time. So just another bit of review. This is what I was just talking about with antenna polarization. This is the large DRG horn. This is shown in vertical polarization, as in the orientation of the elements. So the direction of the elements is called the E plane, the electric field plane, and the direction orthogonal to that is called the H plane, the magnetic field plane. And so then you rotate it 90 degrees, and then that's in horizontal polarization. Again, E plane in the direction of the elements, H plane orthogonal to it. So again, some more review here to anchor things. Mil standard 461G specifies for RE102 antenna positions. I'm just going to read these verbatim. For testing from 200 megahertz up to 1 gigahertz, place the antenna in a sufficient number of positions such that the entire area of each EUT enclosure and the first 35 centimeters of cables and leads interfacing with the EUT enclosure are within the 3 dB beam width of the antenna. So the 35 centimeters of cables is the key thing there. Remember, cables, the big text at the bottom, cables are part of the test article. And so from 200 megahertz up to 1 gigahertz, you need to make sure you're capturing the first 35 centimeters of cable, of all cables and leads, within the 3 dB beam width of the antenna. And for 1 gigahertz and above, you need to include the first 7 centimeters of cables and leads. Okay. Now you might be wondering, why are they only specifying this above 200 megahertz? Well, we'll get to that here shortly. So, and then another bit of review. I promise we'll get to some new stuff here very soon, but just reviewing some of the theoretical session just to anchor us here. So spot size is determined by the 3 dB or half power beam width of the test antenna. And RE102 is specified to be measured at a 1 meter distance from the EUT. When we get to RS103, we have some more, for radiate susceptibility, we have some flexibility there. We can move the antenna back a bit further to get a larger spot size. But for RE102, R equals 1 meter, as I've shown it here. So it's a predefined distance, so we have no flexibility there. But just some examples here. For a 3 dB beam width of 30 degrees, that spot size is just over half a meter. And for 60 degrees, it's a little over a meter. Okay, and it's just basic geometry, right? The 3 dB beam width is specified as, from the extreme angles where you're 3 dB down from your bore sight gain. And so when you get your beam width, whatever that is, that angle 3 dB, you would divide that by 2, take the tangent of it, and then multiply it by 2, because the tangent's just going to give you the radius, right? So then you need to multiply by 2 to get the full diameter of your spot size. So it's just basic geometry, but it's very easy to forget a factor of 2 if you're not paying attention. And cable layout, just the first thing to point out here is that our cables should be per the mil standard, and this is the GEVS modified diagram, but we're following much of the guidance in mil standard 461 that our cables need to be 10 centimeters back from the front edge of the ground plane. So we've got our 10 centimeters there. All right, so we'll start looking at these measurements with different antennas. I'm gonna go back to the camera for just a second here. Okay, everyone seeing the camera display now?
Yeah, I see it.
Okay. So be a little wobbly here, but I want to walk over to the bench. We got the rod antenna disassembled here, but we got some pictures of it in the charts. But all right, thank you. So the rod antenna, comes in these different pieces. The rod itself is right here. I mean, it looks like an old time car antenna, and it unfolds is the right word. Unfurls. I'm not even sure what the word is. Extends out to 41 inches is the specified length if you extend it the full way. Then it screws into a base with a preamp, which is this red box. The input to that preamp is ESD sensitive. So we generally put a piece of copper tape over it when we're not using it. You want to have a wrist strap on when you're putting the rod into the base. And then it has this counterpoise, which you'll see in the picture when we go back to it, it's in these two pieces here. Ideally, I mean, it's a monopole antenna, so an ideal monopole would have an infinite ground plane. How many of you have ever seen one of those? It's a rhetorical question, right? You have to have a finite ground plane, right? The infinite is ideal, but the compromise is, I'm not actually even sure what these dimensions are, if there was any rhyme or reason to it. It looks like about 60 or 70 centimeters. But and then there's a specific way that Mil Standard 461 tells you to connect it to your measurement system, and that's what will be in the slides. So, but it says to connect it through a coaxial cable with a ferrite bead, and I'll have some pictures of that here in a second, and comparing it to the diagram of the Mil Standard and the description of why to do this. And then the coaxial connector mounts to this L bracket, which then you bond to the if you have a ground plane on the base of your floor, on the floor of your chamber, that's ideal. This isn't so much a full ground plane, but we do have these metal strips in the floor. You can point to those. We have these metal strips in the floor that are tied to facility ground, and that's where we tie it, and that's what I'll show you in the pictures here. So I think we can go back to the slides now, show you data that we took with the rod antenna. So, I'm hearing a hot mic, so if you could please mute if you're not asking a question. Okay, so the rod antenna. Are you back? Can you see the slides again now?
Yes.
Okay. First, I want to ask: Is Harry Hodis on the line? Are you out there, Harry? Oh well, I just want to. A fun story is one of the first EMC symposia that I attended. I don't think it was the very first one, but it was number 2 or 3, somewhere in there. I was still kind of getting the lay of the land of what the EMC symposium was all about, and I went to a discussion of specifically about the rod antenna that we're about to talk about, and in a lot of technical subjects, it's always amazed me how people manage to take the really cool work that we do and make it sound mind-numbingly boring. And that's kind of what I've tried to counter that in my presentation style for whatever it's worth. But it was a very dry talk, a very dry presentation about rod antenna measurements, and I do recall kind of drifting off until it was time for question and answer, and Harry was the first one to grab the microphone and made a very impassioned statement about doing rod antenna measurements for 30 years and so on and so forth. So anybody out there know Harry and have any trouble believing what I'm saying?
I know him, and no, I don't have any trouble believing what you're saying.
Okay, there we go. But I always wanted to thank him for first just the immediate thing of waking me up in that session, but also just getting me to see that, okay, like all of the we can be passionate about this stuff, and and especially about doing things properly. And so I'm going to talk about some of the ways, uh, some of the older specified ways of doing these measurements, and why we keep revising or revisiting these test methods, and why the mill standard keeps getting revised, getting updated to address some of the things that have been discovered with these test methods. So anyway, there's just pictures of the rod antenna set up, and pointing at our test article here. One of the things I was going to point out here about a few slides ago when I mentioned they only specify the run of cables that must be included in the 3 dB beam width of the antenna above 200 megahertz. So here the rod antenna is the lowest frequency range that we do RE102. It goes up to 30 megahertz. Does this look like a particularly directional antenna? It's a rather rhetorical question, but anybody? Rob is saying it's very directional.
Yeah.
It is. So how directional is it? It's darn direct. No.
It's got that ground plane.
It's got clearly this is a pretty much an omnidirectional antenna. You don't really have to be too particular about where we put this. I tried having it pointing right directly at the center of the test setup. I clearly missed it a little bit, but this one's pretty forgiving. This is going to see everything that's in front of it. And in front, I mean, that's a relative thing. Like you can turn this in any direction, right? So anyway, broad antenna, the monopole is pretty omnidirectional. So here's a chart or a figure from Mill Standard 462 of specifying how we used to do these measurements. This may well have been one of the topics in that talk that I was talking about, but they specify bond the counterpoise to the ground plane. Maybe a little hard to see here, but they were talking about running a copper strap or what have you, a hunk of metal from the counterpoise all the way to the ground plane where your test article is sitting.
Setup as we use now. But
Okay.
after some reason, we went back to tying it into the table, but quickly went away.
Okay. Well, in G, but I don't know if you guys heard Rob. So you want to say that a little bit louder in case they
I
didn't hear?
was just going to say, every 5 years, obviously, we revise the mill standards. John mentioned mill standard 462, which sister document is mill standard 461C. This same method was used in 461F. And I don't know why it was switched from here to mill standard E, which was grounding it to the ground plane of the chamber. Then we went back to this in F, and then for 461G, we're back to grounding it on the ground plane floor. So Ken Javor probably knows the reason why.
Yeah, I mean, I'm not sure if Ken is on, but there's a lot of history there. Why we went back and forth. And you see this document's dated 1971, but I do have conversations with people who insist on, or we're under contract for such and such document, or that we're doing things per this document or that document. Sometimes there are really good reasons to do things per an earlier version of the standard, as I mentioned in conducted emissions, using CEO3 to measure current. For what we generally do on NAS emissions is far preferred to doing CE102 to measure voltage. I mean, so definitely not knocking going back to earlier standards or earlier just earlier descriptions for how to do things, but pay attention to like documents get updated for a reason. And so in the next slide, I have the excerpt from Mill Standard 461G saying I'll just read this verbatim. This is right from the appendix for RE102. Bonding the counterpoise to the bench ground plane or the floor with a wide strap was found to enhance readings at higher frequencies of the rod and depress readings at other frequencies. floating the counterpoise with the coaxial cable electrically bonded at the floor with a weak ferrite sleeve, lossy with minimum inductance, on the cable produced the best overall results. Lowering the antenna such that the center point of the rod is 120 centimeters above the floor to be consistent with the other antennas improved the results further. So we found this in the early days of JWST when we were going with 461C and 462, that some people found that they were failing RE102 miserably in this frequency range when they were using that older method of bonding the counterpoise to the table. And when they did this more up to date, 461G wasn't even out yet. I think it was I think they were drafting it at the time, but Ken was involved in that, and I think it was the Canadians, I believe, the Canadian Space Agency, were making an appeal of hey, if we do this measurement per the more up to date test method, we pass. Is this okay? And we said yes, by all means, please do that. So just again, things to pay attention to of when a document gets revised, you owe it to yourself to know what's in there. There are a lot of things like this in there that are specifically there to make your life easier. And okay, I'm still hearing a hot mic, so can you please mute unless you're asking a question? Okay, so here is the overall diagram from the mill standard showing layout for all the three major antennas. So we have there's the rod, which we're going to talk about first, and then the biconical, and then there are two double ridge guide horns. So the first thing here is the specification that we're 1 meter from the test setup, and we can see that for the rod, that's to the actual rod, not to the front of the counterpoise. So there's Greg sporting the ruler there. And so we put the rod itself a meter away from our test article, and that's I've defined it to be where the cables are, but strictly speaking, I guess I should have probably moved the box back a little bit to be 10 centimeters from the front of the ground plane. So just something to bear in mind. But we're 1 meter from the test setup boundary, and then also we just read that 120 centimeters. That's specified for all of the antennas. The center point of the antenna is supposed to be 120 centimeters from the floor. Okay, and then your bench is supposed to be 80 to 90 centimeters from the floor. I measured that the other day. I forget the specific number, but it is in that range. I think it's 84 or something. Yeah. So okay. So and then here's what we were just talking about, where you have a ferrite bead on your piece of coaxial cable that runs to the floor, and then the coaxial cable is then connected to this bracket, which is tied to the floor, and that was what was found to counteract the I guess the text in the mill standard didn't specifically mention resonances, but I think that's basically what was happening. You get a resonance from your strap from the counterpoise to the table, and that would give you artificially high readings in that frequency range. Everyone hear that? What's that? Oh, yeah. Go ahead and belt it out, Rob.
So this particular antenna also highlighted the reason why we don't wax the EMI floors, because if you have a wax layer on that floor, you're not going to get good conductivity. And this particular antenna is very sensitive to ESD and electrical potential, so it will ring. So yeah, just make sure your floors are nice and conductive.
Yep. Okay. So if we're going to take some measurements, I want to use some limit as a benchmark, and the only limit in the default curve in the mill standard for space applications that goes all the way down to 10 kilohertz, as in that covers the rod antenna range. Well, I guess these other ones do, but they only go down to 2 megahertz. But this lowest curve is what goes down to 10 kilohertz. So I just figured, okay, that's what I'm going to use as our benchmark here for the measurements that we took. And that's fixed wing external, it says 2 megahertz to 18 gigahertz. It's fixed wing external in helicopters. So that kind of has nothing to do with what we do on spacecraft, but whatever. That's just the limit that I decided to use as our benchmark. Okay. And then you see these other limits are 10 and 20 dB relaxed from that respectively. So that'll just give us some context for what we're looking at here. For just general statement here, all antenna factors, all antenna performance characteristics can be found on the data sheets on their respective vendors. Most, I think, if not all of these antennas we're using today are ETS Lindgren. They're kind of the industry standard for antenna manufacturer. But the antenna factor is shown on the right here. This is what has to be put into your measurement software to take the measured potential, and then this is the correction factor that gives you the electric field that had to have induced the potential that you are measuring directly. And then there's just the picture from the website that does not show the counterpoise, but you can see the preamp. So first set of data we took on the left here. We deliberately left the doors open, those doors that I showed you that are behind me right now. We left those open just see what we'd get, and we left the lights on. And so what we know to be the intentional, or what we know to be the real emissions from our noisy power converter, if I can get my cursor to show up, there we go. That's our fundamental at 400 kilohertz or 410, and then the stream of harmonics following it. So we know this is what's coming from the EUT. But we have this thing down here at 70 kilohertz. I never actually totally discerned what that is, but when we close the door, oh, one other thing, we're using the prescribed mil standard 461G bandwidths. So this full plot gives you those bandwidths. You enter those in, but we use the standard mil standard 461 bandwidths unless there's some particular reason to deviate from that. So then we close the doors, left the lights on, and that 70 kilohertz stuff went down. This other little peak below about 50 kilohertz was still there, but it's very low. We didn't really concern ourselves too much with what that was. I'm not really sure what that 70 kilohertz was, but it was something outside. When we closed the door, it went away. So generally speaking, I tend to think of the door, closing the doors and providing a full shielded chamber, which is what this is supposed to be, would tends to be more effective at higher frequencies, but it certainly knocked down that 70 kilohertz, whatever it was. Well, power supply is still in the room here, but I don't know. I mean, we never really figured out what it was. If it was still a problem, then you'd have to go into, okay, what is, if it was above the limit, then you'd want to spend a little more time figuring out what it was. But here, so the next thing we did was we just turned the lights off. The lights really didn't make any difference. Okay. So which we kind of wouldn't expect, certainly at these frequencies. So this would be our run for the record if this were a real test. But just illustrating that you got to pay attention to the overall configuration. Make sure your doors are closed and sealed and the lights are off and all that kind of stuff. All of that sort of thing can affect your measurements. Now, if we go back to the common mode conducted emissions data that for this same setup, and I showed in a previous session, you can see the relationship between them here. You see the same set of harmonics, the 400 kilohertz harmonics, and so forth. And so we went all the way up to 200 megahertz with those CMCE measurements. So the rod antenna frequency range is a good chunk of it, going up to 30 megahertz here. So we see the same basic contour, including this kind of this uptick here around 20 megahertz or so, 15, 20 megahertz, and then a dip. But I think that the thing to note here is you have this ridiculously and arbitrarily stringent RE102 limit here. I mean, I intentionally picked the most stringent one on there from the mill standard, because in the absence of any guidance, people will just pick one of those limits without necessarily any real rhyme or reason to it. So I just sort of picked the most stringent one to make the point. Well, when you're using that as your benchmark, especially if there are no receivers that you're protecting down here, well, you have this arbitrarily stringent limit, and you've got a 50 to 60 dB problem here. These peaks are good 50, 60 dB above the limit. So if that's your benchmark, you think you've got a 50 or 60 dB problem. But if there are no radio receivers that you're protecting in that range, that's an artificially that's an artificially horrendous problem. I'm not saying this isn't a problem. I mean, this is noisy. We know it's noisy. But if you look at the common mode conducted emissions problem, where you have a more tangible victim of neighboring cables, where crosstalk is your problem, and then with this 50 dB microamps limit as your benchmark, well, using that, now it knocks it down without changing the data at all. It's the same EUT, but looking at it in a different way, now it knocks it down to a more of a 15 or 20 dB problem. These peaks down here, fundamental second harmonic, are about 15 dB above the limit, and then this uptick here is 25 dB above the limit. But this is a much more manageable problem, right? You would need a significant amount of filtering to get this mess down below the limit if this was a real limit that you actually had to meet. So this just underscores why we do common mode conducted emissions below 200 megahertz, because then it's something, well, being a more manageable problem is a byproduct. That's not why we do it. But you have a more tangible victim in the form of neighboring cables, and it's a better defined limit, to address that specific problem, as opposed to just an artificially stringent limit that nobody meets. So, okay, any questions on that? No 50 kilohertz?
Yeah, I don't see that 50 kilohertz spike that you're showing.
Oh, yeah, Rob's pointing out that we don't see the 50 kilohertz or even the 70 kilohertz in the common mode emissions. So that's another benefit to doing, when you're measuring common mode currents up with a current probe, you're much less susceptible to just ambient stuff in the environment, right? When you're making, you're making these I mean, the antenna is designed to pick up whatever is in its vicinity, especially that monopole, which is essentially omnidirectional. Anything in the environment can get picked up and affect your results. Where unless it's actually a current passing through the aperture of that current probe, or something maybe inducing current on the cable you're measuring, you're not going to see it, and you get a cleaner indication of what's really on that cable. All right. So,
hey John, I'm sorry, can you go back to that real quick? Just one quick question. So the relative peak magnitudes are a little different between the fundamentals and the higher frequency stuff in these two different measurements. Is that a concern that we might not, in the right-hand side of the conducted, might not be catching the peaks that are shown in the rod antenna? It's just like the peaks on the left are bigger than the high frequency, and they're smaller than the high frequency peak on the conducted.
Well, I have a whole separate, well, I wrote up an app note on radiated emissions as a function of common mode current, and I'm thinking of doing that as a whole dedicated session. But
okay.
That's an excellent question, but that's worth a whole session all by itself.
Cool. All right, thanks.
So, but all right, so you've planted the seed. I'll make sure I do that session here coming up. Okay, so moving on to the biconical or bow tie antenna. That's what we use from 30 to 200 megahertz. So it's shown here in vertical polarization. Greg entrusted me with the meter stick for this measurement, which, could be dangerous. This is actually the 1.2 meter stick, by the way. Was that James who had that ingenious idea? Good. You have a mic on that so people can actually hear you?
That was one of my contributions to the lab.
Yeah, he took 2 meter sticks and taped them together so that you get a 20 centimeter extension. So that 1.2 meter stick, that's what it is. That tells you that you're 120 centimeters above the floor. So thank you, James. All right, so moving right along, and I'm even wearing my blue lab coat there. So all right, so again, don't be shy about looking stuff up. Go to the website, look up these antenna parameters. The biconical antenna, not too surprising in the H plane. So when it's in the vertical orientation like that, it's essentially omnidirectional. That's what this plot is showing you. Right? It's basically looking. I mean, you can just kind of see it visually, right? It's seeing everything around it in this direction. Okay. I'm also showing the gain curve and the VSWR voltage standing wave ratio. That you can see at the low end here, below about 80 megahertz. It's not a very efficient antenna. So remember in the, I believe it was in the lecture portion of this, or maybe it was in the dipole session, probably both, when I mentioned the difference between directivity and gain. And this is a case where this is a really good example of that, because it's not directive at all, right? It's omnidirectional here in this orientation, so it's not directive at all. But the gain goes way down, right? The gain is not uniform over frequency, even though the directivity is, right? It's very hard to see this, but this is over multiple frequencies here. This is how they'll typically show these polar plots, is that they'll have a different line for each frequency. So it doesn't change much over the frequency range in terms of directivity, but the gain really tanks below 80 megahertz. It's very inefficient for a variety of reasons, and it's not a very good match to 50 ohms at low frequencies. So that's part of what you're seeing here. You have more VSWR, more standing voltage standing wave ratio. High standing wave ratio means an impedance mismatch. So it's a greater mismatch to 50 ohms in that frequency range. So this is a problematic antenna to use. I mean, as long as you're aware of these things and can accommodate them, then that's fine. But it's just, and one other thing I haven't even put in the charts here, but this tends to be the most problematic antenna to use in terms of potential interference, constructive and destructive interference in the lab. Right, this frequency range, 30 megahertz to 200 megahertz, corresponds to wavelengths of 1.5 meters to about 10 meters. Because that kind of sounds like on the same order as the dimensions of a typical EMI lab. Certainly this one, right? This is what, about 4 meters by 5, 3 by 4. So yeah, and remember, it's like you just have to get to a significant fraction of the wavelength for that sort of thing to be to be an issue. So when you're talking like quarter wavelength, you're talking maybe half a meter to about 2 to 3 meters. So 24 feet by 20 feet. Okay. And also the anechoic materials are not the most effective in that frequency range. They tend to kick into gear a few hundred megahertz is when you're really getting good absorption. So it's so the biconical antenna and just the frequency range that it's operating in can really make it problematic if you're really not paying attention to what you're doing. So if you don't have to use it, if you don't have any specific antennas you're protecting on your platform below 200 megahertz, and you're just addressing crosstalk with common mode current measurements, then you can avoid all those problems. But should the need arise for you to use this antenna in a real test campaign, you need to be aware of these things. So here's the antenna factor that you would enter into your measurement software. Now here, I went more to the traditional benchmark that we use for radiated emissions, the fixed wing internal limit, less than 25 meters nose to tail, right? So, even though that this is generally like more for aircraft or what have you, but this tends to be our benchmark line here. In fact, above 200 megahertz outside of receiver notches, that is what's in GEVs, is that line. So just looking at this piece that's in the biconical range from 30 to 200 megahertz. So we have our first plot here, again, with doors open and lights on. And now, because we're at higher frequencies, the harmonics, the 400 kilohertz harmonics, are much more closely spaced. So that's what you're seeing here. And then we turn the lights, or I'm sorry, we close the doors, and we get some reduction in levels here. I think particularly above about 80 to 100 megahertz. And then with the lights off, that doesn't really make much difference. So so again, closing the doors is the biggest factor. And this is all vertical polarization. So then we rotate it to more of its bow tie configuration. So that's horizontal. Now we look at the antenna pattern for the E plane, because now this is what applies when you're in horizontal polarization. So it's not completely bidirectional, but it's more like for any fellow audiophiles out there, which I'm one, at least I used to be a lot more into it than I am now. But like when you hear about a cardioid pattern for a microphone, there's a lot of direct parallels between acoustics and electromagnetics, which is kind of cool. But this is kind of a cardioid pattern. And so it's not fully omnidirectional, but it's still looking at a pretty wide field of view. The worst case beam width in this horizontal polarization or E-plane is about 50 degrees, or about plus or minus 25 degrees from bore sight. But realistically, again, where the mil standard doesn't even specify anything about cable length below 200 megahertz. If we just go back to the picture here, those antenna patterns tend to be far field. And we know we're not in the far field when we've got an antenna that's about 1.5 meters wide sitting 1 meter from our test article, right? I mean, I like this view from behind here because, if you really were to take that at face value and see, let's actually, for the sake of illustration, I'm gonna go back to the camera. Everyone see the camera here? And
Yeah,
everyone
we're
see the
seeing the
camera?
camera.
Yes,
You are?
yes, we see.
Okay.
Yes.
Get the meter stick. Usually over here, right? Yeah. And I want the meter stick, not the James 1.2 meter stick. So I think I put on the chart that the spot size that you're going to get at a distance of 1 meter for a 50-degree beam width is going to be about 50 centimeters, roughly. That's good enough for discussion. So that's about what you're dealing with, right? So taking that at face value, get roughly 20 centimeters on either side of the box. Okay, so we want to get some run of the cable on either side of the box, taking this at face value to the letter of the law. But I mean, just so there you go. There's your 50 centimeters. It's 52 or 53, but ballpark. Well, just looking at that picture of the Bicon where it's spanning almost the entire width of this setup, it's like 1.5 meters. If we take that to the letter of the law and say, well, we got to move the thing, 0.5 meter this way to get this cable and 0.5 meter this way to get this cable. So for a total of 3 antenna positions, I'll go back to the chart now so you can see the picture. Does anybody And you should know by now I'm totally leading the witness here. Total loaded question. Man, wouldn't do that. So just looking at this picture here, does anybody think 2 additional antenna positions to get a good view of this cable and then a good view of this cable, that's worthwhile? Or do you think we're getting a pretty good view of the whole setup right where it is? Oh, Rob wants more positions because more is always better. Right. The EMI lab guys here are saying they get paid by the hour, so they're fine with more antenna positions. But if you are writing the test plan, you know, I think you're okay with that 1 antenna position, right? So, you know, I think that's a pretty good indication of why the mill standard doesn't specify anything below 200 megahertz, because, you know, the monopole we already know is omnidirectional. This thing is omnidirectional in vertical polarization. In horizontal, it's big.
Yes, in this horizontal position, we can go with 1.
Come closer in case they can't.
Vertical?
What's that?
What if you change the position and go vertical? Do you still have the same coverage, or do you need to do multiple antenna positions?
Well, it depends. So everyone hear Rob's question?
No.
Oh. Oh, well, I think the more question was, were you hearing it in the headphones or live? Go ahead and belt it out, Rob.
So looking at this in the horizontal polarization, I'll bite and say, yes, we have absolutely coverage in this configuration. But if we change into our vertical polarization, or we're measuring V fields, do we still need to do 1 position? Yeah, there we go.
There you go.
Looks like
Yeah.
we need 2 there.
Well, I mean, it's omnidirectional. I mean, yes, you're going to get the most, you're going to get the highest level from what your closest point of approach, right? So, but this thing is going to see everything that's in front of it. And for a setup like this, I probably wouldn't bother. If it was a larger setup, like certainly like a system level test or something like that, like a full spacecraft, where instead of just extending roughly 1 meter on either side of bore sight, if it was many meters on either side of bore sight for a full spacecraft, well, you're probably not going to be testing below 200 megahertz anyway. But if you did,
Hope not.
if you were going to do that, I mean, we did that on ISOM.
Yeah.
Then yeah, you might want to use multiple positions.
Yeah.
But again, that's the engineer. That's where engineering comes in. Engineering judgment. Okay, are you comfortable with just a single antenna position that's basically going to see everything that's in front of it? And yeah, the stuff that's at either extreme is a little further away and might give you a little bit of a lower level. But for something like this, the single bicon position, you know, for like a unit level test like this, I would think is more than sufficient.
I was
John?
just saying, for the last few years, I'd say going back from GPM. GPM was the last spacecraft we actually did a rod element or tested at 9 kilohertz. OCI PACE and OSAM, I do believe, it really started at 10 megahertz. But those are really the only projects that are only that have requirements to test below 200 megahertz. Everything nowadays tests above 200 megahertz.
Yeah, I mean, if you have some antenna connected receiver operating in this frequency range, then sure, you need to do this. But if not, your major concern is crosstalk, and common mode currents are the way to address that.
So, John, if
Yes.
the unit under test was the box on the right, would you want to bias towards that as opposed to dead center?
So again, that's a good question. In this case, that's our power supply. You know, and in a real test, that for a radiated test, this would be outside the chamber.
Right.
But this is the power supply, and the actual unit under test is this box in the middle. But if this were the unit under test, then yeah, you would bias toward the box. You'd want to make sure you're getting the entire box plus the first 35 centimeters of cable, at least when you get to 200 megahertz to 1 gigahertz. That's where you would define your antenna positions to cover that.
Okay, thank you.
And yeah, you might be inclined to move this a little bit further over this way if this were the actual unit under test and this was just this is just a resistive load here. So I don't think we really need to. We
Yeah,
wouldn't need a dedicated position just for that. The noise is going to be coming from here. So, or this if this were the actual unit under test. So, so we covered vertical. So there's our bow tie configuration. So yeah, plus minus 25 degrees from bore site. There,
If you tilt the antenna at a 45-degree angle.
well, you don't.
Horizontal and vertical at the same time.
You don't do that. And James gets many demerits for asking that question. There have been tests where people get cute, and I shouldn't even say it, it's not cute, but where you tilt the antenna 45 degrees to get some representation of both horizontal and vertical polarization at the same time, and that's really ill-advised. I mean, if everything passes with flying colors, then you can save a bit of time that way. But if you have any issues at all, you end up having to go to dedicated horizontal and vertical scans to be able to characterize the problem you're addressing. So when I've seen that done, it's not particularly, it doesn't really save time because you end up needing to go to the individual scans anyway. So no, James, don't do that. So, okay, so so here are the horizontal scans. This is actually a bit more noisy because let me go back to the picture here. The vertical is really looking at, well, the vertical component of whatever like the displacement current going between your cables and the ground plane, where the horizontal is looking at the distribution of the current in this direction. And that actually goes to be an interesting question. Kind of surprised nobody asked it, but why don't we do two polarizations with the rod antenna? First of all, like tilting the rod antenna 90 degrees is kind of problematic. I mean, it could be done, but we never do that. Just the whole point is that the distribution of currents in the horizontal direction doesn't happen below 30 megahertz. The wavelengths are much longer than that. What's your thought, Rob?
I was going to say, yes, using the mill standard rod antenna that you were demonstrating in your photos earlier, that is correct. You cannot do that. Before you became chief EMI engineer for the center, we didn't use those monopole antennas because they weren't required by the mill standard. We were actually using the site analysis antennas called a SAS-2A. And they were actually calibrated as a monopole antenna. And yeah, that's what I was leading into, where GPM, they actually had me put that monopole antenna above the spacecraft at a 45-degree angle to take a measurement. Nobody at all was willing to do that antenna configuration but me. So I don't ever want to have to do that again. And it was many levels of stupid.
So don't do the stuff Rob just said.
Yes, please
So,
don't.
but the point is that the rod antenna goes up to 30 megahertz, so that's a wavelength of 10 meters. So you're getting right on the cusp of having some voltage or current distribution in the horizontal direction, but it gets more significant above 30 megahertz. So it's when you get to the biconical range and above, that's when you do the vertical and horizontal polarizations. So the horizontal polarization is going to be affected by AC current distributions in the horizontal direction. Like you're getting into transmission line effects, the current and potential along the length of the cable is not going to be constant. There's going to be some distribution determined by transmission line effects that I discussed ad nauseum in the transmission line session. So that's what you're looking for here, and this is a good illustration of how different the vertical and horizontal polarizations can be. So we're getting, this is approaching 60 dB microvolts per meter. What do we get for vertical? 5, 10 dB lower. So this is like 50 to 55. Okay, so the horizontal is a bit higher, and that's with the doors open. So we close the doors, it goes down a bit, and then turn off the lights. It doesn't really matter too much. So going forward, I didn't do any more with lights off or with lights on or with the doors open. So this just illustrates the point why you close the bloody doors when you're doing a radiated test. And you better do it when you're doing radiated susceptibility, because then your neighbors are probably going to tell you that, you know, you're affecting their computers or what have you. But for radiated emissions, it's definitely going to affect your results. So keep your door closed, make sure everything is shielded.
Those haven't worked.
Okay, so again, bringing back the common mode conducted emissions data for comparison. Earlier, we looked up to 30 megahertz to compare to the rod antenna measurements. Well, here's the biconical antenna range, 30 to 200 megahertz. Well, here we go from, like in the lower part of this for the radiated measurements, we've got on the order of a 20 some dB problem here, right? From about 35 or 34 actually is the limit in the plateau here. So, you know, we got a 25, 30 dB problem here, but looking at just the common mode conducted emissions, it's a couple dB problem. In fact, if this is the worst of your, or if this is the worst of your problem, I mean, we've already addressed this in comparison to the rod antenna, but just looking at this as in comparison to the bicon measurements, if this is your worst problem, it probably isn't one. You know, you can probably get a waiver for that. That's the dreaded W word. I shouldn't say that. But this just shows that when you look at it in terms of potential crosstalk, that the limits that we use, the traditional default radiated emissions limits, are way more stringent than they need to be if your biggest problem is crosstalk. Right? The radiated emissions limits are defined to protect radio receivers, which are by design, you know, they are designed to be very sensitive to very low level radiated signals. So if you meet that default radiated emissions limit, you basically never have a crosstalk problem, which is why there is not a specific test for crosstalk in the MIL standard. Okay. All right, moving on to the double ridge guide antenna. Going back to Greg handling the meter sticks, because he only trusted me so far with the 1.2 meter stick. But again, the 1.2 meter stick for the height, and then the 1 meter stick for the distance from the EUT. So this is that large horn that's out in the hallway, and so you can see, get a sense of how big this thing is. But it's on a cart with wheels, so it's not too bad to move around. And then, yeah, that's vertical polarization. That's horizontal polarization. We'll just go ahead and show the data together. Again, don't be shy about going to the website. They'll give you these polar plots for the 3 dB beam width. It tends to be a function of frequency. Doesn't always vary significantly with frequency, but it will vary a little. In fact, well, so this is the graph that tells you the beam width as a function of frequency. And they give you this data sheet goes all the way up to 2.5 gigahertz, but we're only going up to 1 gigahertz. So just looking in that range, our worst case beam width, if we look at the H plane, the worst case beam width is about plus minus 15 degrees from bore site, so or about 30 degrees. So we use that as our worst case. Well, there again, it's about 53 centimeters at a 1 meter distance. So taking that at face value, we would only be getting about 20 centimeters. This is where we have to pay attention to that 35 centimeters. Okay. So taking this at face value, we'd only be getting, you know, about 20 centimeters or so of the cable on either side of our UT. So to really meet this to the letter of the law, we would probably want two antenna positions. All right. We didn't do that here for the sake of illustration, but that's what you would probably want to do with a real EUT. Okay. Now, if the real EUT was going back to our to this picture here. I guess I didn't get one from behind, but if the EUT were this box here, like Mike asked earlier, then you would just look at, can you get the entire box and 35 centimeters of cable in that 53 centimeter spot size? Yeah.
So when we're using the double bridge guide, why is the measurement from the edge of the horn and not the element itself all the way in the back of the antenna for the 1 meter? I've wondered that for a while, and
I'm
always right there.
not entirely sure of the physical
That's
answer,
how
but
they calibrate the antenna. That's a distance
okay.
reference point. Yeah.
So when they calibrate with the 1 meter distance, okay, I mean, so the ready answer is that's what the mill standard says. I don't like to just say that and say just cause.
Yeah.
But John has the real answer. That's how they're calibrated.
Yeah, that makes sense.
But it does show here that it is to the front edge of the aperture of the
Thanks, John.
antenna. So okay, moving right along. We're back here. All right, data. Yeah, here we go. All right, so now we took some data and the doors were closed, but we didn't do this intentionally, but this was one of those happy accidents for a demonstration. We did a sweep here and we saw this fun little peak at, I can barely read. Just below 700 megahertz. And was it you, Greg, or was it James? It was Greg. Yeah, Greg was taking the scans, and I'm sure I would have gotten there eventually, but Greg said, "Oh, phones are on, right? We need to put our phones in airplane mode." We do that, and boom, that goes away. So just another thing you got to pay attention to, like your phone is a transmitter. So and even with the shielded room, that energy can pick up on any of the cabling or anything that's going into the room, and it can affect your measurement. So laptops, phones, everything needs to go into airplane mode when you're doing these radiated emissions tests. And then when we go to horizontal, lights off, phones off, it looks pretty much the same. Now, one thing I thought I was a little surprised by was how clean this is above 200 megahertz. I expected that our chain of harmonics from our 400 kilohertz clock would still be going on up here. But so then I went back to the Bicon data, and we do indeed have all that noise going on. Grief. But look, right around 100 megahertz, it takes a dive. It goes way down basically to the noise floor. I'm not exactly sure why, but just I mean, you have a 400 kilohertz fundamental, and it's going up to 100 megahertz. 200 megahertz would be the 500th harmonic. So it's about the 250th harmonic. But it's a good illustration that that's not unheard of. I've heard people say that, express skepticism about like the 50th or 60th order harmonic of something. Oh, that can't possibly be. That's preposterous. That cannot happen. Well, yes, it can. And I have seen 1000th order harmonics, and as noisy as this power converter is, I kind of expected that. But it goes up to about 200th or 300th order harmonic, and then just kind of peters out and goes down into the noise floor. So that's fortuitous, but what that tells you is that even this noisy power converter isn't really posing a really significant radiated emissions problem, true radiated emissions problem above 200 megahertz. You got to address all this crap down here for crosstalk, but that's a more manageable problem than, like I say, the 50 or 60 dB problem down in the rod antenna range. So moving right along here. We were down. Oh, you didn't see that notch data. Act surprised when we get there. Okay. All right. So this is kind of the grand finale here. At least in terms of the measured data. So the last antenna here that we're going to show is the small DRG antenna, the 1 to 18 gigahertz vertical polarization. Here is where we only need to include the first 7 centimeters of cable in our spot size, and that's not very that's certainly very doable for what we're dealing with here. And so again, we have our 1.2 meter height, 1 centimeter or 1 meter from the test setup. So here, I didn't bother putting any notes on this. I wanted a more open discussion about this. So here you have a similar set of plots for the polar plots for the 3 dB beam width as a function of frequency, and then here's just on a plot beam width as a function of frequency. Well, if you go what I'd call the brute force method and take the absolute worst case over the frequency range of interest, we're using this from 1 to 18 gigahertz. It's a linear scale, right? So you got to pay attention. Sometimes they put them on a log scale. But so our frequency range is 1 to 18 gigahertz. Well, you see that the beam width takes a nosedive right at the high end here, like about 15 and a half gigahertz. And it goes down to about 10 degrees. So I didn't do the math, but that's a spot size probably just of a few centimeters or whatever, 10 or 15 centimeters. If you were to really take that at face value and apply, set a number of antenna positions based on that spot size, you'd need a fair number of antenna positions to cover the UT and cabling and so forth. And that's likely overkill. Certainly, if you don't have any antennas operating in this frequency range, which is pretty unusual, I don't think I've ever seen anything operating in that range. I mean, so S band is 2 gigahertz, X band is about 8 gigahertz, and so forth. I mean, it could happen if you have something in that frequency range. Then sure, you got to pay attention and then set your antenna positions to cover based on that spot size. But if you don't have antennas operating in that frequency range, you can use your worst case to be something more realistic that's actually in the frequency range you care about. So like if the highest antenna connected receiver that you're using is more like X band at 8 gigahertz, then you can use this as your worst case of 30 to 35 degrees, so that you're making most efficient use of test time and not really compromising anything. Okay, just again, this is where engineering judgment comes into play. Of I can brute force this and set the number of antenna positions based on a 5 centimeter spot size, just to be ridiculous. And then you end up needing 100 antenna positions for full coverage, and it takes you all day to do something that you don't really need to spend that much time doing. Right? If using something more realistic to cover the frequency range you care about enables you to cover things in 1 or 2 antenna positions, that's a much better use of test time. Okay, and we've done this sort of thing, we've done this sort of thing a lot. I mean, we do these scans all the time, and and we set a realistic and practical number of antenna positions based on the frequency range that we really care about. And as long as we're pointing at more or less the center of the test setup, we still get at least some meaningful data up in this frequency range, up in the 15 to 18 gigahertz range. So that's what I wanted to say about that. So we first do our basic sweeps over the whole frequency range. And so on the left is vertical, and there's not a whole lot there, but there is this at 2.4 gig, that's Wi-Fi. and we didn't bother like doing another sweep. It's below the limit, but you know, if we turned off all Wi-Fi, and I don't, that's not just that's probably not just putting computers in airplane mode. I mean, that's like the Wi-Fi in the building. Yeah. So if that were really a problem, if that were above the limit, or you know, if there were any significant concerns about that, you'd have to shut off the Wi-Fi in the building, and that you.
Those all in order.
Okay. I don't know if you can hear Greg, but you know, just you'd have to go to some additional measures, you know, closing all of the doors in the facility, you know, to the control rooms and everything else. But that's outside of that, at least our representative S-band notch right there. And I'll show you the scans in the notch here in just a minute. So the plot on the right is horizontal polarization, and there's a little more stuff here below the our basic limit, and it's outside of our S-band notch. So we kind of get lucky there. I'll come back to these here in a second, but we usually do these. This is our frequency range where we typically have our receiver notches. So just the S-band notch was just our representative one here. So we go and do the notches next. That's where you use a lower bandwidth based on the bandwidth of the operation of the receiver being protected. Right, that needs to come from the provider of the receiver being protected. You know, what is the bandwidth they use in their normal operation? That at least approximately needs to be the bandwidth you use for the measurement. It can't just be arbitrarily low to get the noise floor below the limit. You know, the limit needs to be defined to be realistic based on their measurement bandwidth. So we just arbitrarily, you know, I think 1 kilohertz is a fairly typical bandwidth we use here in this S-band notch. So we use that first. Well, you can see that at least with this representative limit at 20 dB microvolts per meter, and I think that's fairly typical. And I think this was the RST test we used as a template. So at the 1 kilohertz bandwidth, we're fairly comfortably below the limit, about 15 dB. So this is, I just said, well, just for the heck of it, and I'm sure I said heck and not hell because I don't curse when I'm on the job. I said, well, why don't we just bump up the measurement bandwidth to 10 kilohertz just to see if there's any broadband stuff we might have missed here. And the answer is no. I mean, we kick up the measurement bandwidth by a factor of 10. So the noise floor is going to go up by a factor of 10 if everything is truly broadband, if everything's behaving the way as you expect. If there's broadband stuff that your narrowband measurement is missing, then you might see some stuff poking up above the limit here. But it's just something to pay attention to, that if you do a basic scan with a prescribed bandwidth and you're well below the limit, it's sometimes worthwhile to just go ahead and bump up that bandwidth just to verify that you're not missing anything. I mean, I do this sort of thing all the time. These scans are pretty quick, at least if it's a narrowly defined notch. You know, when you actually know your specific frequency allocation and your notch is in a narrow range, this scan takes a few seconds. If it's over a very wide frequency range, then not so much. But if it's a scan that takes a few seconds, there's tremendous value in just saying, well, let's just do it again with a slightly higher bandwidth and just compare the results, even if it's not in your requirements document. Just, you know, just take some additional engineering data just so that, and you include it in your test report, because you never know if that might come in handy later. So with horizontal, pretty much the same story. We start with 1 kilohertz, bump up the bandwidth to 10 kilohertz, and again, there's nothing really surprising in there. Now, it would have been really cool for the purposes of demonstration if we had some junk popping up above the limit here. But if we go back to the basic scans here, we don't, you know, the stuff that is poking up above the noise floor, you know, we did kind of luck out that it's not in this representative S-band notch. But you can't always rely on the luck of the draw. If you do actually have a receiver notch, like right down in here, this stuff down here, that's it's kind of hard to see, but it's 1.55 gigahertz. Well, and it's kind of some broadband stuff there. Some of that is probably landing in one of your GPS receiver notches. So if you do have a GPS receiver on your platform and you do have a notch in that frequency range, that stuff could be a problem for you. And I think that might be from the EUT. There's actually a little indication of it here. I think these two plots were taken at slightly different times. I had to leave, and Greg and James finished up and took that horizontal scan. And I don't know if they came back a little bit later. So something may have been just different enough that we were seeing that junk in the horizontal plots that wasn't in the vertical. So, but for whatever it is, these peaks here are not a problem with respect to the major limit here, the broadband scan with the 1 megahertz bandwidth. But if you have a receiver notch that coincides with any of these peaks, that's going to be a problem, and that's what you're going to have to address. And that's the major thing that you'll have to address, way above and beyond any of the junk that we saw in the RADA antenna range with an arbitrary limit. It's when it's landing in a receiver notch that's a known victim that you have to protect. That's where you have a problem. Does somebody have a question?
No, there was a person waiting.
Oh, okay. I let him in. Okay, that's the extent of the data that I have to share. I was just gonna take a little time to talk about these lonical cog spirals. That's what they are. Conical log spirals. And are you still there, John?
Oh, yes. It's just like tilting a biconical 45 degrees.
Well, I would disagree with that, but we can have that discussion another time. But John and I have had many spirited discussions about these conical log spirals. But and actually, though, that's part of the show and tell. The equipment that's not supposed to be on the bench while we're taking measurements. I'll go back to the camera in a second. But so there are two versions of this in the different frequency ranges. This large one operates, will cover the 200 megahertz to 1 gigahertz range, and it's got a nice wide beam width, plus minus 30 degrees, so a 60 degree 3 dB beam width, and then the higher frequency one, the one that works above a gigahertz. Now it works, I believe it's specified from 1 to 10 gigahertz. So it works over, for most of the frequency range we care about. But if you have any receivers, above 10 gigahertz, and it won't work for you. But this antenna has a beam width of 60 degrees, plus minus 30 degrees, up to about 7 gigahertz. Now, the center of the beam does shift above 7 gigahertz. So again, just something to pay attention to if you are intending to use it in that frequency range. That's the end of the charts, but I think this would be a good time to actually go to the show and tell. You can actually see the large conical antenna right here. You can see my cursor, I'm pointing at it. But can everyone see the camera again?
Yes.
Yeah. Okay, so I don't think it's terribly heavy. Let me kind of heavy, it's just big and bulky. There we go. It's not bad. So this is the large. No, that's not the camera. That is. Okay. Holding it up in front of the DRG antenna. Anyway, this is the large dual ridge guide antenna. This is the one that'll operate from 200 megahertz to 1 gigahertz. You can see that the element, it's got a wire that is just coiled around the cone. So it's circularly polarized. I'm gonna pick up the other one. It's just smaller. It's the same basic construction. It's just smaller and lighter. And then this is much better. This is the higher frequency one. Actually get a little closer. This is the 10 gigahertz model. And like most antennas, it's just got a coaxial connector. That's where you connect your cable and go to your measurement device, your receiver, spectrum analyzer. Any antenna is just converting, radiated field to, if it's a receive antenna, can be used both ways, both for transmit and receive. But as a receive antenna, it's just converting that incident electric field to a potential that you measure here. But and here again, it's got a coil of wire wrapped around the cone, so it's circularly polarized, which means you don't need, horizontal and vertical polarizations. There's no reason to do this. And there's no reason to take two separate measurements. It does more accurately. I think many antennas on your platform are, if they're not this same kind of construction, I think they do tend to be omnidirectional, right? You don't want to have to worry about your spacecraft being horizontally or vertically oriented with respect to the Earth or whatever it's communicating with. I think most antennas on platforms tend to be omnidirectional. So one thing in its favor is that it more accurately represents that. I don't know what else to say about it. When we get to radiated susceptibility, I'll talk some more about that. But one thing is that these can't take a lot of power. I think we actually had one of these on the wall of shame. I don't think it's there anymore. But
Oh, Rick took it down.
Yeah, party pooper. But
Put it in my office though.
I think this thing is limited to 50 watts.
Yes, that's 50 watts, and that is 200 watts, or 250 watts.
Yeah, I think
Actually next to our amplifier for that.
okay.
one.
It's harder to torch that one. We learned how easy it is to torch this one by doing it, on the job training.
Once you exceed the max rating, if you keep applying more and more power, you never get to that max level. You just keep burning it out.
Now, oh god, that's good.
Oh, you broke?
Oh my gosh, no. It's a glue gun thing, and actually, if this tip right here was burnt out, and that's what burnt out on the other one.
Yeah, the end of it turned brown, and
Yeah.
that was what was on the wall of shame.
Yeah, and we had there's a little black mark here on this thing too. So
Oh,
So you think we burnt out both of them?
no, just
So
one.
that-
This is the glue gun, the glue piece. I've been talking to ETS Lindgren about this all morning. It's really just a superficial thing. I just need a glue gun, but we don't have a glue gun here, so it's another one of those things where I'm bringing it in from my house and we'll fix it.
so I didn't break it.
No, that's a James thing all day long. You get a James, had nothing to do with it. It's still James.
Yeah. Well, so don't worry,
Question.
John. I'm getting to the drawbacks.
Question.
What's that?
Yeah, question. Does it matter clockwise, counterclockwise, that when it's assembled this antenna? How
Yes.
it's gonna-
Yes, it does. Actually, let me grab this again. I'm not going to try to put that cap back on, but yeah, the question is, does it matter if it's clockwise or counterclockwise polarized? And yes, it does. It's just the direction that the coil of wire is wrapped around, and I'm not sure how it's defined, whether it's going that way or this way.
That's a right hand twist.
Okay, so
I know that for a fact because the ones that we bought from Ken Bohr has a left hand twist.
okay,
So, and when we were doing shielding effectiveness measurements for the drapes and the other materials, we wanted to see what the long spirals were doing. So we actually did get a right-hand spiral, the right-hand spiral, and a right-hand spiral, the left-hand spiral measurements. And yeah, you can definitely tell you need to have the proper horn measurements when you're using those.
now if you're just measuring the typical DUT that isn't specifically circularly polarized, you're just you're pointing it to just measure what like an EUT like this is pointing out. It shouldn't matter. It won't matter whether you're using right hand or left hand polarization. But if you're doing a specific if it's specific antenna communication or like calibration, if you're using the incorrectly matched if you're using two circularly polarized antennas and they're not matched, then you'll get useless data. I don't know if it'll be, zero, but it'll be much lower than it would be if they're actually matched. So that's the main.
Your signals, I think it just attenuates it.
What's that?
I think you'll still see a signal, it just attenuates it.
But it'll be much lower than it would be if when they're actually when they're matched polarizations. So aside from the higher frequency one being limited to 50 watts, it's limited to being able to. I think we're trying to go to 20 volts per meter with that thing. So it's not suited for levels like that. But if you're testing to 5 volts per meter, it's okay for that.
Yeah.
That's all RS.
I love them for radiated emissions. I do not like them for radiated susceptibility.
For RE, because they have a big beam width, right? If their beam width is big, that means their gain is low. Right, low gain, large beam width, less directional. That means they're not as sensitive. So for like measuring in low level notches, you can't always get there with one of these antennas. So they may be okay to use for the large scans, the full frequency spans, but when you're zooming in on a notch to get to a very low level signal, these might not have the sensitivity to get you there, and you may have to break out this guy right here, the 3115 DRG in this frequency range above a gigahertz. But
just to add in on something from an EMI test lab aspect, if I'm testing a box level test, I am not using those log spiral antennas down here at all. And the primary reason for that is they are really good for not qualifying a boss, but just characterizing to make sure within like family workmanship is at a higher level for boxes and stuff like that. I don't know if John's mentioned this as of yet, but let's see. Can you see that little laser pointer right here? So if you're using the mil standard horn antenna, this horn antenna right here, and I bore sighted right there, that's my measurement. I'm bore sighted there. So I'm taking that plus the 7 centimeters of cable and stuff. The things with these log spirals is it doesn't have a bore sight here. It's taking the measurement, but it's rotating around this little bit of an area. And that's the reason why you do not want to use this antenna on a box level test, because we want to know the exact emissions coming out of those connectors in the box and the slots. When you're at a system level test and you're testing a spacecraft with multiple boxes, we don't care about this little bore sight rotating around, because we're looking for the maximum field of the envelope for what we're trying to measure. So that little bit of rotating isn't an issue. But at a box level with this thing would rotate in and out of the box if we were to do the measurement with this particular antenna. That's all I got.
Yeah, and I hinted at that with the from the data sheet where it showed that the bore sight line does shift over the frequency range.
Yeah.
I think more in particular with the higher frequency one.
Yes.
So now mil standard 461 does specifically say don't use these for a box level test. Now with GEVs, somebody had a comment there. I'll look at that in a second. In GEVs, we say that they are permissible. It's not thou shalt use them. What's that? Everybody still seeing this? Okay. All right. Now the ISS documentation does specifically permit them. So if you're doing an ISS test, you can use these log spirals. So it's not in any way that thou shalt use them. If they're again, every tool is another. It's another option in your toolkit.
The ISS standard though is that it's allowed on an ISS payload, or is it allowed on a box that is on a payload?
I'd have to go back and look to clarify that. Okay. I thought it said you could use them for box level tests.
Okay, but most ISS payloads that I've seen are typically like the size of your house refrigerator.
Yeah.
Which I could see that being a case, like, okay, log spiral that all day long, but it's still, it's a smaller
They're-
box.
They're best used, I think they're most effective or most worth using on a large test article. Like
Yeah.
a full up
especially
payload, full up
with
spacecraft.
I think they're great.
Yeah. Because you got the big full field of view, you get both polarizations at once, you can really significantly reduce your test time on a large test article. I think that's really when they make the most sense to use. But again, it's an option based on the discretion of the test engineer. Right? If you really don't want to use them, nothing says that you have to use them. But they are just an additional tool at your disposal. You have anything to add in the negative column, John, or did I cover it?
Thank you. Yeah, appreciate it. I did have one comment, but I'll do it after the meeting.
Are you sure? Okay.
Yes.
All right. Anyway, just obviously, I mean, I mentioned the passion associated with rod antenna measurements. The log spirals inspire some passion too. So, what's that? Yeah, and Andy, another engineer in the EMI test group here. He's not a fan of the log spirals either. But again, I'm all about passing along information. Just that these are an option. If you do ISS based testing, the ISS documentation does specifically permit the use of log spirals, so you at least should be aware of them and aware of, well, I mean, their benefits and their pitfalls. I mean, there's nothing new about that. I mean, I think it's a common refrain that I try to keep coming back to is every piece of test equipment has its benefits and its limitations. And to run an effective test and to be a good test engineer, you just need to be aware of those. I mean, that's not even just test equipment. Every single device that we use for anything has its limitations. And when you use something for what it's meant to be used for, it works great. And when you go outside that and try to use something when it's for what it's not meant to be used for, well, it doesn't work so great. So you just gotta be aware of the limitations and what it takes to actually use a given piece of equipment most effectively. So that's basically what I have here for radiator emissions. Anybody have any questions, discussion, open discussion?
Already got it there. Yeah, it's another one.
Oh, you can always get another demerit, James. Was your mic hot when you said that?
No. Say it again.
Sure, say it again.
I already got a demerit. That's another one.
But I mean, we always have more demerits for you, James.
Yeah.
Rob says he definitely, has an unlimited supply of demerits for James. So,
That's great for it.
any questions from out there in the peanut gallery?
So this really has covered component level testing with a few references to the spacecraft level, right?
Correct. Yes.
And you do have a philosophy for what's necessary at spacecraft level testing, right?
Yeah, there's a whole section in GEBS about that, and that's probably grounds for another session here. But yeah, that's a large topic that yeah, I think we can cover that separately. But yes, there's the general concepts are, I mean, the general physics is the same. Physics is physics, but you do need to approach a system level test a little bit differently. And that's why I insist on, for one thing, not calling it RE102 or RS103 for rated susceptibility.
Yeah.
The mill standard nomenclature, the mill standard document and the nomenclature are specific to unit level tests. And when anybody says that they're going to run RE102 on an integrated spacecraft, just get out one of those old timey chalkboards and be like Robert Shaw in Jaws. Just do
Yeah.
that for me.
And so we're going to 464 on that one on GOES, right? On GeoXO, I'm sorry. And so
Right.
we've got some transitioning to do to help out with that.
Thing is, I mean, we've discussed this in the working group, but
Yeah.
464 is not terribly explicit. I mean,
Right.
it's got some general guidelines. Like 461 is very explicit. Here's the test method. I mean, it encourages tailoring, right? We tend to tailor the limits more than the test method, but as needed, we will tailor the test method too. But 461 is very explicit, at least about the baseline test methods. Set it up this way, put your current probe here, or set your antenna 1 meter from the test article, and that stuff. There's none of that specificity in 464.
Yeah.
So just if we're saying we're testing to 464, there's some gaps that we have to fill in. So
big gaps, and then get it documented very well with the vendor so that everybody's in agreement going forward, including self-compatibility versus launch vehicle compatibility testing kind of thing. And that's the big thing. So maybe another session.
Yeah, definitely another session. I think what I was planning to cover next was probably radiated susceptibility, again at unit level. I think radiated emissions and susceptibility and self-compat, I think I can roll those all into one session. So that's what I'll gear up for. I hadn't really thought that far ahead. I was thinking in particular
system level.
Yeah. System level RERS and radiated susceptibility. I can cover those all in one session. I was thinking particularly for these sessions specifically about unit level test methods, like from Mil Standard 461 and GEBS. But
yeah,
that's certainly a worthwhile thing I can throw in.
Right? It's huge because you've got all the workmanship that you did to get the boxes built and cables built. But then when you put it all together, you can have workmanship problems where they didn't do something right.
Correct.
And the next thing you know, you got a problem. Okay.
So, and so what Mike just said is quite is quite key. Workmanship. We hear all the time that the EMI is just a design test. Like, no, it is also workmanship. I mean, it's certainly a design test, right? But you're also looking at workmanship, and testing at the system level, like you did everything absolutely correctly, at all the lower levels, you put everything together as a system, you shouldn't have any problems. But should is another one of my least favorite words in the English language, right? You put everything together, there is some checking you need to do to make sure everything is indeed put together properly. And sometimes you find things that you need to address, and you'd rather find them than not, right? Than just launch something and hope for the best. We'd never dream of doing a thing like that, now would we?
We don't dream.
I was just thinking we tend to do no harm. Try not to.
Yeah, I mean there are some do no harm payloads, whatever, but yeah, but point taken, Mike. I think I will. I have all the source material for that. I just need to pull it together. But that'll be a little further down the road. I'm going to do RS and want to cover CS 115 and 116, which I think I can do those in one session.
Do you want to this is really high level, but do you want to maybe highlight two different types of programs? One that has a good EMI box level program where we tested all of our boxes. So when we got to the spacecraft level, we're just checking our boxes, testing workmanship. versus another project that did little box testing. You get to a spacecraft level, and then next thing you know, you're trying to figure out common mode issues that should have been addressed at a box. I mean, we got some test campaigns that have taken us 20 to 30 days to complete, and then we've had Class A missions that are in L2 right now that we did in 8 days, less than 8 days.
The general take on that is don't follow what was behind door number 2 as you've defined them there. You know, just don't do the thing of slapping everything together and only doing a system test. Now, people do that, so sure, I guess that's worth addressing.
Those tests.
Right.
But you had a ton of incidents, I'll call it that, on JWST, right? Where,
yeah,
holy crap, you found this at the system level kind of stuff.
But we did plenty of box level testing. It wasn't like we just threw everything together. And the stuff that we found at system level, I'd have to go back in my memory banks here, but I don't think there was anything we found at the system level that like we should have found with a box level test. It was like, oh, well, what's that?
Yeah.
Here's why you do it.
Right. But you know, you do these tests at the box level to beat down that risk. Like if you're finding stuff, I mean, you find stuff at the system level all the time, but if you're finding stuff at the system level that you really should have found or you could have found with a box level test, then definitely shame on you. Like that's why we do these tests at the lower level, is to give ourselves the best chance of finding these things and addressing them when it's a much more manageable problem. We have pulled boxes off of spacecraft to fix, you know, whether they're EMI problems or just any other electrical problems. And I don't think there's anybody on this call that's had that experience that's gonna say that didn't suck. I mean, use a technical term, right?
Yeah.
That having to pull boxes off of an integrated platform is not pretty. I mean, it's additional risk, and managers really don't like it. You know, it's very expensive, and it's a huge schedule hit. You know, all the rest of that, where you've got a box. You know, nobody likes finding a problem anywhere, right? But if it's a box level test, you find the problem right here, you're in the best possible position to go, oh, okay, we need to fix that. And you know, we've had that happen where, okay, it takes a couple weeks, maybe even a month or two. I think the one RST box a little over a year ago, I think that was a good month or 6 week hit, but it was the flight computer turning off initially when we found the problem for no explicable reason. We did eventually find the reason and all that. That's another story. I think I might have mentioned that in the CS 101 session actually, but
the one with the copper tape in the middle of nowhere.
No,
We'll talk about
no. But that was the flight computer shutting off for initially no explicable reason. It took, I think everyone on the project came around pretty quickly to, no, we need to fix this. We can't have transient events shutting down our flight computer, you know, at some random surprise time in the middle of the mission. That's kind of not where we want to be.
Yeah.
Right? Not everything is at that level. You find some things that are like, all right, this is going to be a minor inconvenience that might happen a couple times during the mission. We can live with this. That was one that was pretty clear. We ought to fix this one. So, but that's the thing, you want to find that during a unit level test because I mean, yes, that was the flight computer and it was delayed getting integrated on the spacecraft by, you know, I mean, it became critical path. And there was a lot of testing on the spacecraft that they couldn't do until they got it installed and integrated. But I think they were able to do some things to at least make some use of that time. You know, it wasn't necessarily a full 6 week delay in the overall schedule. But when you have a problem that you're finding at integrated system level, then everything is day to day, by and large, right? You know, if you're talking about pulling a box off of an integrated platform and then doing further diagnosis and fixing an EMI problem, whatever, even, you know, EMI, electrical, whatever the problem is, that's extremely painful and it's a day-to-day slip, and you've got, you know, management is riding your case until the problem's solved. As I mean, there's no getting around that. That's the way it's going to be. Preaching to the choir, I'm sure, but
yeah.
Anyway,
so thank you.
Yep, sure. Okay, anybody else have any questions before we call it good for this one? You want another demerit, James?
There's no way to give him another demerit.
We love James, just for the record, but anyway.
I'll give James shit.
Okay, well, thank you all. And I should point out, I'm going to be traveling this week to deal with one of these kind of problems I was just talking about at an unnamed university in another city. They actually got travel orders through the system for me. But I'm going to be going to visit this unnamed university to help them address problems where they basically ignored all EMI concerns, and they're wondering why they're failing EMI so spectacularly. So I'm gonna be heading out tomorrow. So no session on Wednesday. And the one of the major reasons I have moved my retirement date out was to support the RST platform level EMI test. The first phase of that is scheduled to start possibly as early as this weekend. And it's on second shift, right?
Setup might actually take place Thursday, second shift. That's something I'm trying to confirm right now, but I just talked to Nick. But yeah, they're still looking at Friday, Saturday, Sunday.
Okay. Well, if it's Friday, Saturday, Sunday on second shift, rest assured I will not be doing one of these sessions on Monday morning. So it heads up that we will probably not have any of these sessions next week, but we'll pick up the week after if that happens. But I'll send emails out with updates.
Have sessions with Justin James if they like.
You can do that.
John,
all right.
One other thing I meant to say is for the system level test for self-compatibility, we're going to be using the spacecraft's antennas for doing the detection, which is unusual. So yeah, that kind of pros and cons of that, but it has to be in the design at the start of the mission to be able to do that. Otherwise you miss your opportunity to get that into the plan, right?
If you're talking about tapping off of the spacecraft antenna to go to a test receiver to see what the receiver is seeing. Yeah. You need to have that designed into the platform if you're going to do that. And I think I haven't worked in the military domain, but I think DoD platforms tend to do that. I think it's maybe more typical, at least than on NASA platforms, but I can't say that for certain.
Okay.
But yeah, we can talk about that when we plunge into self-compatibility. Okay. Anybody else have any parting thoughts? All right. Thank you. Have a good week, and I'll be in touch.
Thank you.
Thanks, John.
Thanks, John.